Hello, let's enjoy computing more complicated Gaussian functions. So, oops, that's like this. So for example, let's consider an integral where I'm integrating e to minus x squared, and then I have some e to alpha x. And this alpha could in principle be a complex number. So what happens here? What is this e to I alpha? If alpha is purely imaginary, which means that alpha is equals to I and then modulus of alpha. So this is the set of purely imaginary real numbers. Then this is the Fourier transform. In this case, I of the integral, which depends on alpha, is the Fourier transform to minus I alpha of e to minus x squared. If alpha is real, then we have a shifted integral, and this we could view, for example, as a convolution. Then e of alpha is an appropriate convolution. Let me write it like this: Gaussian convolution with some sigma of the function e alpha x. So what's going on? We would be having the exponential function, and then everywhere along of that function, we would be integrating it with a Gaussian filter function. So the new function at x, so we are integrating out the variable x and we have alpha, but then again, we can plot alpha on the real line. And then this will be smoothing the exponential function in some way. This one is already smooth, so this integral will be quite simple. So those are the two regimes. And then an interesting regime is the intermediate case. Alpha is equal to x plus iy, where xy are both non-zero. In this case, what we have is in some way a combination of both those things. So we should view the complex plane x, y, and then the x0, y0. And then here we have the value, so we would be having the integral e integral plus iy is dx e to minus x squared e to I y x times e to, we did x0, y0, y0 here, x0, x. So we have a combination of both those things. This will be a Fourier transform, a Fourier transform of a shifted Gaussian kernel. Okay, so let's start computing those things. So for example, let us compute that alpha being real. So over the entire real line, dx e to minus x squared e to alpha x, alpha times x. And all those integrals depend on the capability of being able to bring this into, again, a Gaussian form. So the ingredients will be one, bring to Gaussian form, two, shift variables, three, compute Gaussian integral. So we will see that this is a stage of simplification, something messy. Suddenly we will put it into a standard form. Maybe let's call it standard Gaussian form. Then, well, this is maybe not standard yet. Okay, let's see whether we will call it standard or not. Anyway, let's consider a function like this, x minus alpha x. What do I need to do to write this as x minus alpha half squared? Well, I will need to subtract alpha squared divided by 4. Let's check that this works. X squared minus 2 alpha over 2, so alpha, and then times x plus alpha squared minus alpha squared over 4. So this is correct. Which means that this integral is a purely Gaussian integral and then there is a constant, a multiplicative constant. A multiplicative constant means that I can factor out here something that doesn't depend on the integral. Which means that I have a Gaussian integral times a Gaussian function. So this is what we call form number 1. The next thing is to shift variables. So let me shift the variables. Maybe I can fit this on a page. Okay, let me define y is equals to x minus alpha half. dy is equals to dx. And when x is equals to infinity, then y is also plus minus infinity, which means that my integral here, I of alpha, I can write this as again over the real line. Nothing happened here because the real line is infinite, dy e2 minus y squared, and the multiplicative constant stays. And I have e2 minus alpha over 4. Good. So next we are using that this is pi, and then e2 minus alpha over 4. Good. So we have computed this integral, which means that a Gaussian convolution of an exponential function is a Gaussian function. And why is that? Well, an exponential function of this form, if alpha is positive, is growing very fast. However, exactly when this is growing, as we were discussing in the first video, the Gaussian function is decaying very fast. So by monotonicity of the exponential function, e2 minus x squared is actually smaller than e2 minus x. And by doing those transformation, we actually prove that it's actually much, much faster decaying because it's exponentially small here, the entire integral. So if you sum up all those products on the way, they don't blow up. we don't become infinite. So for x smaller or equal than 1. Well, let's make it strict. In this case, we want a strict argument. Strict means it's a sharp inequality, and here as well, because we want to say that this is decaying. So this is how we can interpret this. And what happens there? You see that this is essentially almost the line. It's not exactly a constant line, but it's almost a line here. And then it decays so fast that this becomes smaller. So what happens here is that I have basically, I'm summing up this interval where this function is non-trivial, and here it roughly has this value, e2 minus alpha squared. Alpha, yeah. So it's basically summing up this function here. Okay, well, you can maybe think about it and disagree. But the important thing is that the decay of the Gaussian function allows us to convolute even at an exponential. Then here it's approximate, the product is approximately 0. So the Gaussian function filters out a portion of the exponential function around here. And when you sum this over in this relevant interval, well, if you do it over the infinite line, then this will be decaying with alpha. And one thing that is counterintuitive is that if alpha is growing faster, so we had integral over r dx e2 minus x squared e2 minus alpha x. And this one is square root pi minus alpha squared divided by 4. So there's a counterintuitive thing in this result that if I have one exponential function and a fixed Gaussian function, and then let me take another exponential function with a much, much higher alpha, then you would think, okay, this grows much faster, then the Gaussian convolution should be bigger. But in this picture, you see that the relevant interval is smaller. How to see that? So this is a bit counterintuitive, right? So what is this value? When alpha is larger, then this grows faster. So we are in this pink region here. And then the joint integral seems to be smaller than it was before. Why would that be true? So subtracting here. Okay, this needs to be plus. Okay. It makes sense. Makes sense. So we are summing this up like this, but we are summing up always more stuff. So this works. Okay. Correct. So it actually diverges. Very good. Very good. That's fun. Okay. Picture is sometimes helpful. Okay.